Okay, so we can start with the first speaker of today. She's Anna Dall'Acqua from the University of Ulm, and she will talk about on the free boundary elastic flow.
Thank you very much to the organizers for the possibility to be here, for the kind invitation. It's always a pleasure to be in Pisa. Sorry that I just arrived yesterday evening and I missed already 2 days of this conference, but due to teaching, I couldn't earlier. So what I'm speaking about is joint work with Manuel Schlier, that now is a postdoc at the University of Salzburg, and he was a student, so did his PhD in my group this year. So I'm speaking about the elastic flow. So I'm working on these subjects in several years, and now with Manuel we made a step forward, studying also the free boundary. But let me introduce a bit what's the subject of the talk is. So in the following, E denotes either a compact interval in R, or when we are speaking of closed curves, simply the unit circle, and we consider gamma a smooth immersion from I to Rn. And here n is a dimension bigger or equal than 2. So that is a smooth immersion. For such curves, we define the elastic energy as the integral over the curvature squared, integrating along the curve. So the curvature, as we all know, curvature, can we compute it at the second derivative of the immersion with respect to r lengths. So here ds is defined as the derivative with respect to the arc length parametrization. This is called elastic energy. This is a very old energy. It started already with Bernoulli when he introduced, one of the Bernoulli brothers introduced a model, a variational model to describe an elastic rod. So very, very old, but it's used also nowadays. Also, it has many applications for imaging, for instance, and it appears also in several situations like limit of kind of elastic energy. But I'm not interested on the application, the derivation, just looking at the energy and studying. What we are going to do is to study the gradient flow of this energy in a particular situation. This energy can be seen as a one-dimensional version of the Willmore energy, since it depends on the curvature square. But it's very different. In particular, we can see that looking at the behavior with respect to scaling. So if we look at the energy of a curve now scaled by a parameter big R, like a radius, so we take the curve and we scale it by R, then the elastic energy behaves like 1 over R, the energy of gamma, so it's not invariant, and there is scaling. And we immediately see via this calculation that if we look at the infimum of this energy among immersions, let's say now of closed curves, this infimum is simply 0, because we can reach 0 simply by scaling, taking R to infinity, and it's not attained. So in order to make that a nice variational problem, what we will need is to get rid in some way of this behavior, the fact that via scaling, making the curve bigger, we let the energy get arbitrarily small. We have to get rid of this behavior and the scaling, and a possibility will be to penalize the length or to fix the length. And today we will work with fixed length. So just to fix that. Okay, so that is about the energy. If we fix the length, then the infimum is attained, and it is attained by a circle. So a nice variational problem where under constraint of fixed length, the circle is as the minimizer. Okay, so now what we want to go is to the evolution problem associated to this energy. More specifically, we want to look at the L2 gradient flow. And that is called the elastic flow, or we call it the elastic flow. So the L2 gradient flow is of the elastic energy. So we look now at a family of immersion, depending now on time, defined on this interval I with values n Rn. And the evolution equation is that the curve changes in time in the direction of minus the gradient of the elastic energy. And let me add immediately with the right sign additional term that I will explain immediately. So motivated by the variational problem, we see in order to get a nice existence of a minimizer, we need to fix to add some constraint in order to take under control this scaling. And this we do here with a Lagrange multiplier. And this, the Lagrange multiplier may take several values, several forms, and I will discuss that in a minute. So, but let me write what this is once. So that is minus twice the derivative of the curvature with respect to arc length, and of that only the orthogonal part minus k square k plus lambda gamma k, where this orthogonal part of the derivative means for a phi defined on the curve, we take the projection of the derivative orthogonal to the tangent to the curve. So that's due to the fact that it's a geometric energy, what we are looking here, so it's invariant anti-reparametrization, and this invariance appear here also in the PDE in the role with this with the existence of this projection that gives us that in one direction we get less information from the PDE. Okay, so what is which kind of PDE is that? That is a fourth order quasi-linear evolution equation, parabolic equation, let's say. Okay, what about this lambda? Depending on the choice of lambda, we have different kinds of elastic flow. So if we choose lambda of gamma identically equal to 0, then we speak of free elastic flow. So we follow the gradient, the L2 gradient of the elastic energy without any control on the length. Another possibility will be to take lambda of gamma constantly equal to lambda, some positive parameter, and that will be penalizes the length. So so the evolution equation decreases the elastic energy of the curve, but at the same time, we add to the energy function a term depending on the length, so that along the L2 flow, also the length is going to be controlled. And that is called the length penalized. The other possibility is that the lambda of gamma is really, quasi-linear. It means that the some derivative, not the highest order one, appear in a non-linear fashion. So here we can think of the curvature is like a second order derivative, for instance, and here you have second order derivative to the third power. Okay, so fully non-linear. So fully non-linear, the difference will be when the fourth order derivative will appear in a non-linear way. That doesn't happen here. The fourth order derivative appears in a linear way, but lower order derivative appear at some power in a non-linear way. That I mean by quasi-linear. And that happens, we can see it immediately, for instance, in that term here, where the second order derivative appear to the power kind of 3. Yeah. You're welcome. Thank you for asking. And then the last, so another possibility will be that this lambda is really a Lagrange multiplier that enforce what I already told you that we are interested in, enforce that along the evolution, the length of the curves is kept fixed. And then this takes the form of 1 over the elastic energy of gamma, the integral of the L2 gradient of the elastic energy scalar product with the curvature. And that is the length preserving elastic flow. So taking this lambda, this equation became the length preserving elastic flow. Today, we are going to speak about this third situation. So we choose along the talk, during the talk, the lambda will be given by this expression, where here the gradient, you can read the formula from this equality here. So that is the choice of lambda that we do. What does that in turn gives us in the equation? In the equation, this choice of lambda gives us a non-local term here. So we have a non-local contribution. So by this choice, taking this choice. And that's what we are going to do today. Right. So study about elastic flow. So if, there are a lot of persons that have been, okay, I moved the wrong one, sorry. There has been a lot of people working on the elastic flow. So so let me just put a list of names that is, there are not all, but just to tell you that, so it started already in the 90s with Polden, Venn, Koizo, so separately gave contribution. Then very fundamental work, it's the work by Juk, Kubert, and Schätzle. So that's me. So I write all among commas because there are several combination of the authors, so I just write all the name. So this paper of Juk, Kubert, and Schätzle has been fundamental in the study of the elastic flow for closed curves, where they studied all three kinds of flow, and they were able to prove long time existence. And in the case, not in the first case where it's not expected, but in the other two cases, then even subconvergence to a critical point. And then there are a lot of other contributions, so Matteo, Novaga, Okabe. Let me write also Röger, with Schätzle, that they studied the application, some gamma limit that gave rise to the elastic energy. Then there is Chun-Chun Lee, Paola Pozzi, Glenn Wheeler, McCoy. Then there are some younger generation, Spena, Rupp, Müller. Yeah, good, younger generation, Garke. Sorry. Please, it's recorded, super. Menzel, Pluda, ja, Pozzetta und Mantegazza. Also, Schlierf. Yeah, okay, now I stop. No? So, a lot. So what is still interesting? There are still open problems. There is things interesting, still things to understand. Yes. So I really like, for instance, then I forgot one that I shouldn't. Miura, and then. So, for instance, we already spoke that there's a fourth order equation. That means method based on comparison principle, maximum principle cannot be applied. So all information about qualitative behavior of the solution needs to be needs to be achieved with other methods. And for instance, Müller and Rupp, and also together with Miura, they found some energy threshold below which the fact that the elastic energy is below its threshold allows us to say that the curves need to be embedded. So a kind of Li-Yau inequality for the elastic energy. Very nice is also a recent work of Miura that addresses a question by Huysken about migration of the elastic flow. So Huysken asked, so elastic flow force order, no maximum principle. Is there an elastic flow where you start from a curve on the upper half plane, or the half space, that then migrates in the lower one? And as such, the question is still open, but Miura made an enormous, gave an enormous contribution in the direction. He was able to use result on the elastic flow with Dirichlet boundary condition and gave an initial datum. Yeah, so now, don't take that as a qualitative, it's just to say an initial data that satisfies some Dirichlet boundary condition on the x-axis, that's the initial datum, and then it showed that along the time, so as time goes by, the solution will all stay in the lower half plane, so really migrating. So and that is a contribution of last year, so things are really happening. And that's perhaps a change. So here in the beginning, the stress was specifically on closed curves, and now one is looking more at curves with boundary conditions. So to study the flow with curves satisfying some boundary condition. And so far, very little was known about free boundaries problems. Last year, there were two contributions. The one was by Diana. I didn't write it here. Let me write it now here. She studied the elastic flow of curves that are forced to start and end in a half line. The point on the line is free, and they need to have curvature equal to 0 at the boundary point. And then she studied the elastic flow in this situation. And then there is another contribution by Gazzvani and McCoy, where they studied a cone, and then they studied an initial datum that has to be to stay the end point on the sides of the cone, and orthogonal. So something like that. That will be the initial datum. And they studied the elastic flow for this situation in this cone. And the contribution of Manuel and mine is in this direction. So we want to study the elastic flow under free boundary conditions. And we try to generalize the cone situation. A cone is flat. Can we allow here for something non-flat? And that was our aim. So what do we mean by free boundary? Which is the free boundary problem we are interested in. So here we are looking at a curve gamma from, so now we are definitively piece of curves defined in the interval -1, 1 with value in Rn. So no closed anymore, curve anymore. And now, so instead of a cone, we want here to allow for an hypersurface. So let M subset of Rn, so be an embedded hypersurface in Rn. Hypersurface. So we don't need it to be compact, but it might be compact. What we need is some control of the geometry of M. So either it's, for instance, we need that is so a control on the tubular neighborhood of this hypersurface. So for today, let's think that M is compact, but that's not needed. So what we will need in general will be some uniformly embeddedness of this hypersurface in Rn. Okay, that is our M. That's where the curve is going to sit. So to start and end. And let the node by N its unit normal field. Okay, and then we say that gamma satisfies free boundary condition if. So three things. First, the starting point and the end point needs to lie on the hypersurface. Then we want orthogonality. So we want that the scalar product between the tangent vector of gamma and the endpoint and the normal vector is equal to plus or minus 1. So in absolute value, this should be equal to 1. Okay, is that enough? No. So we have a fourth order problem here. We are not fixing the position. It's just that the starting point and the end point need to be in this hypersurface. So we need to add a further boundary condition to have a chance to have a well-posed problem. And the third boundary condition we add is a so-called natural boundary condition. So that is the boundary condition that minimizer, global minimizer satisfying these two conditions will have to satisfy. So where do we get this third natural boundary condition? Before doing that, let me do small picture. So let's will be our M. So we are asking that our curves start in a point here and end in a point here, and so orthogonally, for instance, like that. We are not prescribing that it needs to start going outwards, could also go inwards, right? We are fixing here just that the tangential vector, the normal vector are parallel, that they don't need to be on the same direction in either of the 2 points. So let me call also the scalar product that has value plus or minus 1, let's call it E plus minus, plus for plus 1 and minus for minus 1. Okay, so this natural boundary condition we can get from the first variation. So if we take variations of curves such that the first order is given by a normal part V plus a tangential part, so that is a normal with respect to the curve gamma. Then let's look how does the first variation look like. Can you read if I write here? Yeah, it's very good. Elastic energy of gamma epsilon in epsilon equal to 0. Okay, so we know the first part is going to be the Euler-Lagrange equation in weak form. So let me write it like that. So that's the part we know. We computed before. That will be the L2 gradient. Let's write it down. The L2 gradient of the elastic energy. That should be a nabla. Okay, plus, and now there are coming up boundary terms due to the fact that we have a curve with boundary points. Okay, so which are the boundary terms? These are twice the scalar product of the curvature with the orthogonal part of the derivative of the normal part of the variation minus twice ds perp k d plus phi k square that computed in minus 1 and 1. So these are the new part coming up due to the fact that now we have this boundary. And now let's see what can we say about these boundary terms. So the first observation is that the term depending on phi is not there. Why is that? Okay, since gamma epsilon, so the variation has to satisfy the free boundary, that means at the point plus minus 1 has to be on our hypersurface M. That means that when we take the derivative with respect, we take the variation, since that has to stay in the hypersurfaces, that need to be an element of the tangential space in the point 0, gamma epsilon, let's say 0 of M. So need to be tangential. No? So we are looking there at the picture, the variation has to keep on M, so the direction of the variation has to be tangential. But then, what does it say now for the variation? So the variation is V normal plus phi tangential. What do we know about the direction of the tangent? The S gamma is parallel to the normal. So since okay, so from that follows that phi of plus minus 1 has to be equal to 0, because the variation first order has a normal part to the curve plus tangential part to the curve. The part that is tangential to the curve is normal to the hypersurface due to the free boundary. That means in order to this condition to be satisfied, then phi needs to be equal to 0 at the boundary point. So this part is not appearing there, and then it means these two terms, now we still have to understand those. We have so far just used one boundary condition, that the endpoints need to lie in the hypersurface. We have still the second one, that is the orthogonality from ds gamma epsilon plus minus 1 equal to E plus minus n gamma epsilon plus minus 1. We take here the derivative with respect to epsilon, and put epsilon equal to 0, so that the condition is to first order satisfied. Then from that, we get that the derivative of the normal part of the variation in the point plus minus 1, that is simply a constant, plus or the minus 1. The derivative of the normal is the shape operator times the curvature. Okay, so that's the second condition. The normal part of the variation has to be equal to the shape operator applied to the curvature, and then we go here, we apply this condition, and then we see that we get as extra boundary condition, natural boundary condition, that the orthogonal part of the derivative of the curvature at the endpoint has to be equal to the shape operator applied to the curvature. And that's the other boundary condition. So in other words, so that's the natural boundary condition that appears from the variational problem, and that's the extra boundary condition we put on our PDE in order to have a well-posed problem, with the hope that now the problem is at least geometrically well posed. So the problem, sorry. So the problem we are looking at is the elastic flow. 1 dt gamma is equal to minus twice kappa minus kappa square kappa plus lambda gamma kappa, together with a suitable initial datum. And then we have the free boundary condition, the starting point and the end point needs to be on the hypersurface. The tangential vector scalar product with the normal to the hypersurface is equal to either 1 or -1. And the third condition is that the orthogonal part, the derivative with respect to arc length of the curvature is equal to shape operator applied to the curvature. So that's also in ±1. Okay, so that's the system, so the PDE we are looking at for gamma, our immersion. Gamma 0 is some initial data that satisfy the free boundary condition. So our main result is the following. So let gamma 0 satisfy the free boundary condition, and let's assume that this elastic energy is strict positive. What does it mean? So, and smooth, sufficiently smooth. I don't go in detail. Yes. Right, that's the point. So from the variation, these are information we get as possible variation that to first order keep the free boundary condition. And then we go back here and we want that the boundary term goes to 0. As you said, that the boundary term vanishes, and this gives us this boundary condition on kappa. So for each V that satisfy normal variation, that satisfy this equation at the boundary, in order to have a critical point, we need this to hold at the boundary. So that's the third order, that's only at the boundary point, right? So the third order derivative of gamma, or first order derivative of the curvature, has to equal shape operator, yes. It's, yeah. Yes, okay. So we start from an initial datum that satisfies the free boundary condition and with positive elastic energy. So we don't want to have a straight line. So this is the condition we have there. Then there exists a solution for some time. Maximal solution of 1 for some time. Moreover, so now what we would like to have global existence. For most example of elastic flow that we know, we have most cases always that the solution exists for all times, different from as curve shortening its flow and so on. But here we cannot get so far global existence. We have two situations can happen similarly like in the case of networks. Moreover, either the infimum over time of the difference between the lengths of the initial datum, let us recall the length is kept fixed along the evolution, so that is the length of gamma of t for every t, minus the distance between the endpoints of the curve is equal to 0. So either along the flow, as long as the curve approaches the straight line. So that's the length of the initial datum. This we could call also as L of gamma of t, because we are looking at the length preserved elastic flow. That means the length is kept fixed along the flow. So either along the flow, the distance between the endpoint of the curves is equal to the length that we have fixed. That means in some sense the curve approaches a straight line. Or if that does not happen, then we have global existence. So there is a bad case that we cannot control this situation when the curve along the flow at certain point approaches the straight line. But if that does not happen, if that does not happen, then the solution is global. So we have global existence for the solution. And once we have that, then we can, as usual, the global existence, then we can show that up to reparametrization, subconvergence, subsequences, and translation, we have convergence to a critical point of the elastic energy. And here, in this case, we have convergence to a straight line. That's the no. So that's I wanted to comment on that. So that's the big thing. Can we? I hope that I can tell you where this condition comes from, and it's really a technical situation, a technical detail that we cannot yet do differently. So I don't know if that happens in finite time, if it can happen, or in infinite time, or if that doesn't happen at all. So no idea. Yeah. So far. In the first case, there exists a sequence of time going to t that we don't know. It might be that we don't know, finite or infinite, no idea, such that gamma of tj converges to a straight line. So a straight line segment, to be precise, in C1 alpha. So just in C1 alpha. After reparametrization, translation, and up to a subsequence. In the second case, for any sequence tj going to infinity, gamma tj converges to an elastica, so a critical point of the elastic functional, up to subsequence, reparametrization, and translation. Yeah, it possibly translation. Okay, so which is idea of the proof. So for of the solution or of the limit of the solution, yeah. Yes, so geometric. Yeah. Yes. Yeah. Richtig, right. Yeah. With free boundary. Okay. With. Yeah, because we can. Yeah. Sorry. Well, so we had convergence is high norm so that we can control up. It's one dimensional. That means up to the third order. Okay. Idea of the proof. Yes. So yeah. It's a nice proof. So now I don't, I will say. There is first short-time existence. One needs here a nice short-time existence result that can be used then also in the for the proof of global existence. And here we work with maximal regularity. More precisely, we start with an initial datum in this space for p bigger than 5. That ensures yes. So yeah, because everything is 0, right? Yes. Yeah. If we have, nothing happens. Yeah. Again, yeah. Yeah. Okay, why this big P? Because that is embeds in C3, so that we can really make sense of the third order boundary condition in the usual sense. Then we need some control of the reparametrization, and then the point is the long time existence, and here one uses energy estimate, energy estimates, interpolation inequality, plus interpolation, plus then for the subconvergence some abelians lemma. Okay, but so that is a bit of technical. If you are interested, you can look at the picture. It's the picture, not at the paper. Why do we need this no straightening? So what does go wrong when the length, when the end point, when our curve approaches the straight line? What's the problem? The problem is the Lagrange multiplier. So we have this Lagrange multiplier, this non-locality in the equation. This non-locality is not a problem for the short-time existence because it's of lower order, so compactness, no problem. But for the long-time existence, is well known already from the seminal work of Schönlieb and Schätzle that this Lagrange multiplier is critical in the energy estimate. In the sense that if one tries to control the Lagrange multiplier directly via interpolation, we don't gain anything. So it's exactly the critical power. There is no space, no epsilon that we can win there. And then there was the trick that go back again by Schönlieb and Schätzle, that using the fact that we have a gradient flow. So, the behavior of the elastic energy with respect to scaling. So the idea is using the idea that the behavior of the elastic, so using scaling, they were able to get an estimate of the Lagrange multiplier, some constant plus the L2 norm of, of dt gamma plus some terms with the curvature in some norm. That's not so important. That is good for the interpolation. And what is good about this term taken to the squared is integrable in time. Squared integrable in time. Integrable, oh, come on, so this term taken to the squared is integrable in time. And this allows us to get, to win in the Gromwald, so to apply still a Gromwald, lemma of Gromwald argument that gives us control. Good. Okay, now with the boundary condition, you cannot really do scaling, but we know from the proof idea behind the positive identity, scaling correspond like testing the equation with the solution. So the idea is instead of behaving with scaling, we can test the equation. So for boundary condition, the idea will be do the same by testing with the solution, with F, with testing, with gamma, sorry, yeah, by testing with gamma. It's like scaling correspond with testing on gamma. What's the problem? We have boundary condition. So every time we take partial integration, we lose. That means we cannot simply test with gamma. We get to take away something that makes so that the boundary condition goes to 0 plus a correction so that this thing is 0 at the boundary. And this correction should be a best linear because then we don't have any other contribution. And what do? We take the straight line. And then to get the information, we need that this test function is not 0. Or the contribution coming from this function is not 0. Like exactly this condition get lost when this infimum goes to 0. Okay, so that's why straightening. Is the straightening a problem? Generally not. So if, for instance, M is flat, then straightening does not happen. Straightening does not happen. So because M is flat, we need to start and end orthogonally, so there is no way we are going to satisfy the boundary condition by a straight line. Or when M is the boundary of a convex set, and with the right choice of orthogonality in the initial datum, that also straightening is not going to happen. So straightening appears, so due to the free boundary, we really need to have an hypersurface that allows that the length that we describe is attained by a straight line segment that is orthogonal to the boundary. So that's really a special situation. So generically, it does not happen. Yes. Yeah, this might happen when we take.
Here's the boundary of ball.
Yes, plus I said it, I didn't write. We need the choice of, so we start the orthogonality, the direction of the orthogonality is kept from the initial datum. So if from a sphere, if I start like that, then I'm dead. But if I start so, then everything is fine. So plus convexity alone is not sufficient. You're right. I said it.
No, because it's normal.
Because it's normal. Yeah. But so we can plus the fixed length, that of course, and that you are right, that gives a lower bound than k square, from Fenchel. Yes. Okay, so that is to convince you that so this straightening, so we don't know if it happens, but it's certainly not a generic situation. And do we have more than oh, okay. No, okay. Then I would like to give you another couple of pictures. Sorry, I always try to move the unmovable. So there is a situation in which we can understand a bit more what's happening, and that's the flat case in the plane. So it's a small observation, but allows me to end the talk with some pictures. Right. So what is not yet so good about our main theorem? What is not so good is that we have convergence up to subsequence. So at the moment, the limit we are approaching might depend on the sequence we are taking. And of course, we want to get rid of that. And there is a case where we can't get rid of this situation with simple observation. And that's the case when M is in the plane is a straight line. Always so. Yeah. Okay, so that's our M, the straight line R squared. And the idea is we start from an initial datum, and it has to start on this straight line, has to be orthogonal. So, for instance, das gar nicht so schlecht. Something like that. Okay. And now that's our natural boundary condition also what help us. In the case that M is flat, the shape operator is trivial, so actually the condition here when M is flat is that the third order, so the derivative of the curvature is actually 0 when M flat. And what is then the observation? We can reflect the curve with respect to the axis. Get a closed curve. And this is good. That is a smooth enough curve because due to the orthogonality condition here, we have a 90 degree. Here we have also a 90 degree. So the second order. Now the derivative, we can see that this is kind of saying that the third derivative is 0. That means that taking the odd extension, we have also in C3 continuous. So we are in C3. That means that gives a nice closed curve for this curve with twice the length, okay, but fixed length. This we can let flow with elastic flow with prescribed length for closed curve, and then we know by the theory that that converges. So T is infinity, global existence, plus we have convergence thanks to the Lobachevich-Simon inequality to two possibility. Winding number different from 0, then we converge to a circle, multiple covered. Winding number 0, we converge to the figure 8. In this case, might be better perhaps that I draw it like that, I think. So case of winding number 0, at least that's our understanding. Winding number different from 0, because that's a topological invariant along the flow. So closing, we know what it happens, and then thanks to the uniqueness of the solution, we know the symmetry is kept along the evolution, this symmetry here. That means that for our free boundaries, so if we start from a curve like that or other curves that we know also, straightening does not happen, this we knew already. T is infinity, we knew, but now we know that we have even also convergence either to a certain amount of circle and half circle, depending of the winding number of the closed curve, or the figure 8, perhaps only half of the figure 8, or the 1.5, or the 3.5, or whatever. And so in this case, we know really what's happened. So we can go away from the sub-convergent, really good get full convergence. So we can really, we know where the flow goes to. Yes. And perhaps, so what we would like now to do, several things. So that's kind of the start. Not just in this special case, we would like to go from sub-convergence to convergence. So can we really say that the limit does not depend from the sequence? Then, of course, the big project, the great question, can we get rid of that or understand if that happens or not happened? So that's the big thing. I think it will be nice to study also the obstacle problem associated to this case. So now starting, let's say we have omega, so M is the boundary of convex set. We start outside, we are not allowed to go inside. Which flow can we do, and so on. But that's for the future. Thank you very much for your attention.
Thanks for the nice talk. Are there questions? Okay.
Hi, very nice talk. So
Thank you.
for this business with a straight line, one thing you may have already tried would be, I mean, okay, if there's a possibility of a straight line by the boundary conditions, you could try to linearize the equation around the line and see sort of whether you get exponential convergence or maybe convergence in finite time to this.
Yeah.
I mean, have you
Not really, not
this?
yet, not really. So yeah, we are now. Yeah, but that's yeah, something we should try to. Yeah.
So at the last you mentioned that your curve is out. For example, if M is a unit sphere, you draw a picture which is you erase it. The curve is outside the sphere, but at the last you mentioned that is it possible to study the curve inside the ball?
Yes. So
It's unknown.
Yeah. So and in my flow, so it might start outside. It can get inside, no control. It can get so the only. So that's from the application point of view, perhaps that's not, there is the hypersurface, and I use this hypersurface only at the boundary. The flow then do what he wants. He doesn't see this existence of this hypersurface where there is flow. So that's what is doing our flow at the moment, and that's perhaps not so physical, and that we would like to add like an obstacle that it cannot penetrate if it starts outside, or that if it starts inside that it cannot get outside. But this we didn't do yet. So the presence of the hypersurfaces is seen only at the boundary point by the flow, and then the curve evolves and doesn't know that there is a hypersurface. So that's but as a start.
So another maybe naive. So if the initial curve is convex, is it know that it will preserve along the flow?
So since it's a piece of a curve, that's difficult. But
Codimension one, for instance, for the codimension one, I mean, a curve in R2 embedded, for example, the initial.
Those curves you're thinking, yeah. It's about convexity. I don't know. No result about embeddedness or non-embeddedness. Yes.
Okay. So another question, if not free boundary, for example, if you have a contact angle with the M non-orthogonal, is it possible to ask the similar question?
I think what we did with the orthogonal, you can do also with other angle. Yes, you can try, but then yes, yeah. And I presume then you will get some difference here, or well, here that's a choice, right? That's a choice we made to take this third order boundary condition. This additional we make here a choice. No? We take the natural boundary condition. One could also study the same problem with another choice here.
If the angle is constant, that kind of natural boundary condition can derive the
I should do. I'm always very careful. I should do the computation again, but I think that's what something.
Then I think you have to use you have to use a different variational problem if you want that the contact angle is the natural boundary condition. You have to put, I guess, Antoni will know this in a microsecond, but you probably have to put some additional surface energy on the surface. Then you can probably get a non 90-degree angle as the natural boundary condition.
And you can also prescribe it and get different third order boundary conditions.
Yeah.
Okay, thank you.
Yeah.
Okay.
I have the same question on the angle, because when you move away from 90-degree, instead of having two essential, you just have one essential boundary condition. and therefore you would expect two natural ones in 3D for a curve in 3D.
You are not fixing the eye contact angle, or
You're fixing it, but that just means in terms of a graph representation, saying that the derivative has a certain length.
Yeah, you are right.
And that's not, instead of being 0, which means you lose one dimension in your essential boundary condition, which means you have to gain one dimension in your natural boundary condition. So it may,
yeah,
the nature may change.
yeah. So we started with, yeah. Oh, that's right. So.
Thanks for the talk. You started with this, or you added this constraint of having the lengths preserved, and then you give some overview of all the results and so on. Could you comment maybe briefly what would change if you have a stronger constraint on local inextensibility?
I didn't work yet on that. There are some colleagues, I think Okabe did some works on that. So I don't feel prepared now yet to give you. I was in a conference that it might be so it seems to be from the application point of view quite the more natural things to do. But I personally didn't yet work on that, and so now I have difficult, so I cannot say more than that. But I think it might be something to look at.
Like total lengths to be constant, and can you not always read?
So yeah.
That is locally parameterized by arc lengths.
In that case, then one shouldn't take the fixed length.
But the dynamic is different.
Then one should look at the penalization.
Yeah. You didn't say that when you talked about short time existence. Do you need to take a gauge, so to speak? I mean, you have sort of freedom of reparameterization.
I use it. So yes. So we choose. Well, here is off. Yeah. So, but I think.
Well, I know that the evolution is different. So I mean, if you say that this doesn't have any effect on the analysis, I would be surprised. But,
no, but I mean, is it really different, or is it just sort of?
No, it's really.
Whether you follow the reparameter. So you're telling me you don't just get sort of different parameterizations, but you get different shapes.
Yeah.
Lambda.
Yeah, lambda is a field and not a constant anymore.
Yeah. Okay.
Okay.
Yeah. So, but that's something, to look at. Thanks.
Yeah, maybe the last question.
Okay, thanks. I actually had the same comment as Stefan, and I think maybe a linearization might work, say, generically. I was wondering whether for M analytic, there might be a version of the Lojevic which might also help there.
So thank you for the question. So we are working on it. So at our understanding, and there is also a group, so I think Antione and Diana is also working in an application. So Fabian Rupp, so Lojevic inequality is important from going from subconvergence to convergence. Analyticity is in several points necessary for Lojevic. So here we will need Simon Lojevic inequality for a problem with constraint. And when we have constraint with finite dimensions, so like fixed length, fixed area, this we know how to do the Lojevic-Simon inequality that gives so this approach that has been done by Rupp works with that constraint with finite codimension, and that what we will need here, due to the free boundary condition, we need a Lojevic-Simon inequality for problems where the constraint had not finite codimension. And we are working with that, and we are finishing up. So I hope soon to have it. And we, as an application, we have the not the elastic flow, but we do the Wilmore flow for free boundary. And that's near local minima is that will be still a first contribution, but we are working on that. So that's we needed, so several things needed to be changed. So it's so mean this in our approach. Yeah, thank you.
Thank you.
Okay, so we thank Anna again. Okay, so the next speaker is Carola Bibiane Schönlieb from the University of Cambridge, and she will talk about structure preserving deep learning insights from analysis.
Okay, thank you so much to the organizers for having me here, especially given the circumstances so that I can really only be here today. So my apologies for that, but there are some strict boundary conditions with my mother turning 80 this week. So before I start, a lot of memories actually came to me when I came here this morning. One is again connected actually to Matteo, because as I just told Matteo in the break, the last time I've been here is almost 20 years ago when I was just starting my PhD. And I was talking about the Cahn-Hilliard equation at the time, so quite different to the topic today. But that might also give you some background about where I'm coming from. And the other thing, the other thought I had is connected to the rain. So when I gave my very first plenary talk, and Simon might remember this, in Hong Kong at the SIAM Imaging conference, probably 15 years ago or something like that, it was raining so heavily the night before that my shoes got completely wet, and so I couldn't wear them on the next day. I needed to give my plenary in flip-flops, which was extremely embarrassing. And today I couldn't change my shoes, so they're wet. Well, okay, so before I start, I always like to thank my research group in Cambridge. Everything that I'm going to tell you about is really due to these wonderful people. And I would like to thank them, and of course also the collaborators that have worked with us on what I'm going to tell you. And I'm acknowledging them on the way. So what I'm going to talk about is structure preserving deep learning. And this has been a topic that has really kept us engaged for the last, past kind of short history, last couple of years, as a topic where deep learning or recent advances, let's say more generally in data science, really offer opportunities for mathematicians for solving problems differently. But also the other way around, that mathematics or insights from mathematics allow you to design neural networks that come with provable guarantees, and that, for instance, allow you to say something about the stability of neural networks or something like that. And here you have 3 boxes that give you some overview of topics that appear in this context. So first of all, maybe I should say structure preserving deep learning refers to designing neural networks or to train neural networks with some structural constraints that either come from facts that you know about the solution you want to approximate with the neural network, or as I said, that come by desirable properties you want to impose. And it usually also appears, a lot of times when you hear people talk about neural networks, it's very tempting to just use them as a black box. But this talk is very different to that, in that either the application you're after just doesn't work if you use neural networks as a black box, because you would need an unreasonable amount of training data to really practically make it work and also generalize to unseen scenarios, or because you have a reason why you want to impose certain constraints. Now, inverse problems is a big area in mathematics where you're measuring something that is not directly what you're interested in, but the solution is indirectly hidden in it, either through here, I'm just modeling it through a linear operator or a nonlinear operator. So it could be, like in this case, X-ray tomography, what you're measuring are X-rays or the energy that's still that you're measuring on the other side when the X-ray passes through objects like the human body, for instance. And from that, you want to reconstruct a physical object, like the inside of the abdomen, like in this case. And so in this case, deep learning had a big effect on how we solve these inverse problems, because prior information that we impose on the solution determines very crucially how accurately you can compute, in this case, the inside of the human body. So anything that you can model about the kind of solution properties that you think your image in this case contains, the better. And here our modeling capacity paired with what you can computationally efficiently compute has limited us in the past with just analysis-based solutions. So the idea to learn here something from training data, to learn structural properties about the solution from training data, makes a lot of sense conceptually, but also practically. People have shown that we can really create a step change in the quality of solutions for these type of problems. The other area is, if you wish to forward to this inverse scenario, where you want to solve, for instance, partial differential equations, or indeed discover dynamics or discover differential equations from data. So here, again, neural networks have been, in various different approaches and settings, been applied. Again, in order to make this work, in order to have guarantees about the solution qualities, the qualities of the solutions that you compute, you need to impose certain structures in your neural network solutions. And then the last box is more generically about the fact when you want to impose certain properties on neural networks because you want to have guarantees about their efficiency, their stability, or accuracy, for instance. Okay, maybe just to say, a couple of years ago, it's now outdated, but the main ideas, I think, are still the same. We wrote a paper with some colleagues from NTNU in Trondheim, which talk a little bit about structure preserving deep learning and its different aspects. Now, I want to zoom now into one of these boxes, which is structure preserving deep learning for inverse problems. And here, again, I usually like to present things with a macro view and then zoom in. The macro view is more or less like this when you think about structure preservation in this context. How do people design structure preserving deep learning approaches for solving inverse problems? Is either what I call here deep learning into mathematics, so starting with a mathematical model. A classical mathematical model for solving inverse problems is, for instance, variational regularization. And using the neural network or the data-driven component in a plug-and-play fashion, so replacing some parts of this mathematical model with a neural network. Or mathematics into deep learning, which is you model the solution from the outset as the output of a neural network, and you use your mathematical modeling and analysis, numerical analysis skills to design the neural network, so to parameterize the neural network in a way such that, again, you get some solution guarantees at the end. Well, it's both about solution guarantees, but also, again, the more prior information, the more you constrain your data-driven model, it's also very, generally speaking, correlates with the amount of training data that you need. So, which makes sense. The more, the less parameters you have in your model, the less training data you need to capture the landscape of solutions you want to approximate. So what are, well, and maybe here, so this is variational regularization. This is the second category where this is called learned iterative reconstruction, where you design the neural networks or the layers of your neural network, having conceptually in mind how your iterates would look if you, for instance, solve this variational regularization problem. So you have the gradient or the subgradient of this regularizer here, and then the gradient of the discrepancy term. But then you change, you completely parameterize this, and you change in every iteration what your regularization procedure and what your discrepancy term is. And they don't really appear, well, depending on what type of model you have, they appear more or less explicitly. But that's how, you know, where this is coming from. What are the constraints that usually pop up if you do one or the other? So one, Lipschitzness is a big one that appears very often, that you need that. Convexity is a nice one, especially if, again, the solution of your inverse problem in the end boils down to solving a variational problem. And then maybe you have some additional properties, physical properties about the solution that you want to impose, like mass, volume, or positivity preservation. And then there might be some additional conditions that just come from your forward operator, from properties from your forward operator that you would like to make sure your solution fulfills or is aware of. So starting with the first box, which is the one that we have mainly worked in, so the deep learning into mathematics, starting out with variational regularization model. Most of you probably have encountered this, well, for different things maybe, but just to motivate this from an inverse problems viewpoint. So again, the inverse problem that we are working in for this talk is a linear one. So you have measurements y, and you want to reconstruct mostly an image. You can think of an image u. Both of them at the moment just live in generic function spaces x and y that will be adapted depending on how you choose the rest of your model. And the solving this inverse problem, yeah, and you have your forward operator capital T that I said is linear from x to y. And usually the situation is complicated because you have corruptions in the data like noise. Oftentimes in the type of applications that I'm working in, which is in imaging, you also have undersampled measurements. You have less measurements than unknowns. And the forward operators that appear in imaging are usually not are you know, like the run-on transform is a compact operator, so it's usually not you cannot invert it in a continuous way, especially if you have noise. You run into instabilities because of that. So what people do is to try to approximate a solution to this equation on top by a minimizer of an energy functional that usually consists of two parts. I kind of alluded to this already on the previous slide. You have a regularization term that is weighted by a positive scalar alpha that determines how much you want to regularize, how much you want to impose. This is really the term that imposes all the, what we can think of in this talk as structural properties on the solution. And then you have a second term that basically is a quantification of this of your equation that you started out with. So think of this, for instance, the most commonly used term is just an L2 squared term, so a least squares fit between the measurements and your forward model. And mostly, I would say, alpha is chosen with respect to the noise level in your data, so how much noise you actually have in your measurements. How do people classically impose structural properties in solutions? So again, most of the inverse problems that we have looked at, and most of the inverse problems in general that people are looking at, what you get at the end is an image. And most of the time, what happens in the medical domain or the scientific domain, what people are most interested in this image is to quantify something on the basis of it. And in order to quantify something on by means of this image, abrupt changes, or what in imaging is also called edges between different objects that you see in this image are very, very important to preserve. Which in particular means that edge preserving type of regularization approaches like total variation regularization have been extremely successful in this domain. I would say one of the most successful approaches next to wavelets or multi-resolution analysis type of regularizers that people have used as well. Okay, now the object of interest for a structure preserving deep learning approach in this talk is really this regularization term. And the reason is that it really very crucially determines how your solution looks like. Yeah? So what you see here, most of the time in this talk, all the examples I'm showing you are going to be for X-ray CT, which means your forward operator capital T is the X-ray radon transform. Here we are in the situation of sparse angle X-ray CT, which means you're in this underdetermined setting where you have less measurements than unknowns. And what you see here are 3 different reconstructions based on X-ray tomography measurements, where the only difference between those 3 is the regularization that I'm using here in this variational model. So here actually this you can think of as an unregularized reconstruction is actually not a solution of a variational regularization problem. It's a so-called direct reconstruction method, which is minimizing just the least squares fit with a minimal norm constraint. So the pseudo-inverse. And then you have here 2 regularized reconstruction, one with total variation, and now one as a teaser in a way with a learned regularizer. And this is basically the main message here. All 3 reconstructions explain the data in exactly the same way, but the regularization is different. The prior information you're putting into is different. And again, how, the ways we have tried to model how images look like have taken us to a certain position, which is a position actually that is rather good, right? So really beating total variation regularization is not that easy, or any kind of mathematically modeled regularization that has this L1 structures, this L1 structure to it. But you can, in particular in the fine details, be more accurate if you are really targeting your regularization to the images that you want to reconstruct. And this make sense, right? Okay, maybe I was thinking I can catch us up on time because I only have 40 slides, which is very unusual for me. But I shouldn't get lost too much in the slides. Okay, so this is why I want to talk about learning this regularizer within a variational model, and I want to talk about this in this context of deep learning into mathematics. So sticking to the variational model because of a number of things, right? Because if I, in the end, solve my inverse problem in this variational context, plus the fact that I've imposed sufficient properties when I learn this regularizer, then I'm back in the classical variation regularization setting, and I can just you know I can just borrow all the results that have been derived from there. The other good thing is that I have explicitly in there the fit to the data, which again with pure neural network type of approaches is very, very difficult to achieve. Only most of the time with post-processing that you impose consistency with the data so that your solution can really explain the data. And also noise statistics. Noise statistics is usually something that goes into the choice of this data discrepancy term, which again I can still impose here explicitly. So this is the reason why I want to do that. And the motivation for at all thinking about this, why do we need, why do we need this additional accuracy? I think actually I'm showing this example, but I don't think it's for classical CT so important. Actually, this is a bit of a constructed example because in medical CT that you get in the clinic is not undersampled, right? This is usually not sparse angle or something like this. It's usually fully sampled and actually also moderate amount of noise. The real reason are technologies and application areas where the data is much worse. Okay, so one, for instance, to stick to the medical domain, is that there is a lot of development now around portable low-field MRI scanners, where the measurements are by constructions much worse than in the usual clinical MRI. But this also in particular means that because you have high quality measurements from the usual MRI paired with these newly emerging technologies, you can think of a learning scenario that you can create in this context because you can create a training data set. So here I think this is very promising. And the other thing so this is something that, for instance, at Oulu, Andreas Hauptmann managed to get some funding now for them to create their own low-field MRI scanner, which is great because the current manufacturers are not very good in sharing their data. And the other one is ultra-low dose CT is something that we started thinking about with clinical collaborators, Jonathan Weir-McCall and Ebis Sala, actually I should add her here, from Cambridge, and Sam Stranks, who is in chemical engineering, thinking about how far can you lower the X-ray dose in CT and still produce images which are diagnostically interesting. And lowering the X-ray dose correlates with the amount of noise that you have in the measurements. Yeah? So this is one scenario. And why is this interesting? Because the more you can lower the X-ray dose, the more widespread you can make CT available to cases where you just send people in for screening to the hospital. So lowering the dose to an amount that is almost not harmful. Maybe, as you know, our clinical collaborators said, they would like to have this as low as a transatlantic flight. Then it's fine, which is much lower than what is currently being done. This is why this is interesting from the application point of view. And the other one is in settings where inverse problems appear with with a lot of noise in them, like in molecular biology. This is cryo-electron microscopy, where you want to reconstruct atomic structures of proteins from electron microscopy measurements. These are extremely high noise measurements because you can't shoot a lot of energy onto these specimens because otherwise they die. Okay. Yes. So they sorry? Yeah, but then you burn them, and so you can't. Yeah. Okay, sorry. Yeah, so maybe that. But you burn them, and then you can't look at their structure anymore. Yeah. Okay, so we have worked on learning a regularizer for quite some time now, and this more or less, I think, is where we converged now. So I think this is more or less the end point of at least our work on this. Which is this learned weakly convex regularizers for inverse problems. So this is what I'm going to talk about now. The first question that arises when you think about making a regularizer data-driven is how to train such a regularizer. And if you want to have a regularizer that you put back into such a variational model, the thing that came to us was to train it almost like a classifier. Okay, so meaning that you would like the regularizer to pick within the set of least square solutions the ones which favor, let's say, high resolution, noise-free examples of images from your domain of application over noisy, lower resolved reconstructions. Okay. And first of all, if you want to do it somehow like this, you need to think how to create such a training set where you have desirable, what I call desirable and undesirable examples. And this depends on your application. You can either simulate your desirable examples, or you have, like for instance, in the low field MRI example, you have one setting where you can create very, very high quality measurements, like with normal MRI. Or you have phantoms that you can scan to high resolution, and so on and so forth. So you created a training set of the desirable examples, and then you created a training set of the undesirable examples. And again, it depends a bit on your application, but you could, what we did, and actually almost all the things that we have done, is just to approximate what we think is undesirable by a baseline reconstruction. Like for instance, in the case if you have a linear forward operator by the pseudo-inverse reconstruction, okay? Based on the data that you typically measure and that you want to apply this variational regularization approach to, okay? And so if you train it as a classifier in this variational context, it means that if R is fed with desirable examples, it should be small. And if it's fed with undesirable examples, it should be large. And this is also explains the objective that we have used, which is the one Wasserstein distance. That it's exactly the one Wasserstein distance, has different motivations. One is also that this has been used for training neural networks in a particular setting, which is called generative adversarial networks, where the Wasserstein distance has been used to discriminate between real and made up, so meaning produced by the neural network examples, and also by the fact that if we trained a regularizer like this, so meaning that we want it to be here large for examples that come from the noisy distribution, and here I take the expectation, so I want this to be on average, as well as doing the same for the undesirable examples that were the distribution here called PR. If I do this in both cases on average, it means that I actually don't need the training set here and training set here to be paired and to have exactly the same object on either side, which in inverse problems is actually quite a nice thing to have, because most of the time in practical settings, our collaborators in these other domains, they can't give us this. So paired to exactly the measurements that they have taken with their device of interest. Okay, so this is the objective we use for the regularizer. And how do neural networks come in? They come in and how we parameterize this regularizer R. And here also, so this is also where the structure preservation in a way comes in directly in how you design the neural network, because you can now reflect the properties you want to have on R in the neural network parameterization that you are choosing. So what we started out with was very naive, just an off-the-shelf convolutional neural network, and that gave rise to the first instance of what we called the adversarial regularizer, just because it has been trained in this adversarial manner, but also meant that the variational regularization problem we ended up with in the end was non-convex. And we actually also in that case needed to add a little L2 squared term to make it even bounded from below. Then we went to the other extreme and we imposed convexity. One big thing in structure preservation and deep learning is you have a certain property you want to impose, but you want the neural network still to be as expressive as possible. And finding exactly the kind of sweet spot with these two objectives in mind is very, very hard. So for instance, here, this convex parameterization of neural networks that we used then, and since then there have been made some improvements, but not so much, is too constraining. Yeah, so it's not the network that you get is not very rich, which meant also that the results that you got there were actually not that exciting. The variational model was nice because you could solve it very quickly, but you didn't gain so much from the data-driven regularizer. And then, iteratively, we approached this weakly convex setting where we parameterized the regularizer with a weakly convex neural network. Let me just jump over this because I kind of said that already. So, which means, so just to remind people what this means, a function is weakly convex or rho weakly convex if you add as an L2 squared term with the multiplier rho, you can turn it to be convex. And there is a nice characterization of weakly convex functions, which is that you can write them as a composition of a convex function and a smooth function. Okay, which is exactly what we did for setting up the neural network. It's just a composition of a smooth neural network and this convex input, what is called input convex neural network, that we used here in our convex adversarial regularizer. And why is weak convexity at all an interesting thing? So, well, first of all, you have some nice approximation properties. So it does actually approximate a reasonable class of functions. And then you also gain something in when you solve the variational problem afterwards, you can create iterative algorithms that have convergence properties. okay, which was really the problem also with a purely non-convex regularizer we started out with. Okay, so how does it work? So this is now an example with the same abdominal scan data that we had at the beginning, which comes from the Mayo Clinic. We had some training data in this, so everything here was simulated. We had the normal dose, fully sampled reconstructions from 10 patients in this data set, which we divided in 9 for training, 1 patient for testing. And then we simulated from that this sparse view setting where you undersample the measurements. And also we added some more noise to it. The reconstructions that you will see now in comparison is filtered back projection, so the unregularized reconstruction, total variation regularization as a non-learned representative. Then the adversarial weakly convex regularizer. And then this one here is learned primal dual, which is kind of I think the gold standard now in deep learning for inverse problem, is the one that usually achieves the best results and belongs to the second category where you design neural networks with some mathematical properties in mind. The really crucial difference between those two is that here, because you are still in a variational setting, you have the important solution guarantees like existence, continuity of solutions, and also again convergence of your iterative scheme. Whereas in this setting, you have actually almost no guarantees. Unfortunately, this nut hasn't been cracked yet, although it works very well. This algorithm. Ground truth is, as I said, this is all simulated. So this is the fully sampled normal dose CT slice. And this is the reconstructed one with this method. And what you see here in terms of the numbers is just a way to quantify how well you match this ground truth image. This is the peak signal to noise ratio. So it's a kind of inverted L2 distance between the two. And this is the structure. So this means the higher this is, the better. And this is a structural similarity index measure, which is between 0 and 1, as a bit more of a sophisticated measure that is computed in patches that are slided over the image, and so is also taking into account a little bit more of local properties of your solution, rather than just integrating over it. Okay. This is what you get with total variation regularization. Looks exactly like you think TV should look like. This is what you get with the weakly convex regularizer. So you can exactly see what I said at the beginning, that you gain a bit in the small details here. And this is what you get with learned primal dual, which is qualitatively almost the same. It looks a bit blurry here, but actually more or less it's kind of the same, particularly again having in mind that you don't want to have pretty images to look at, but just the ones to quantify something. So almost the same, but as I said, the difference is that we have some theory here, and it is not important. I'm jumping over this because I said this already, but this is more or less why we like the variational setting, because we just inherit all the theory that comes from the classical inverse problems literature like Engel, Hanke, Neubauer, and so on. We just inherit that. What else can we say about this regularizer? Well, this is actually still old. This is the work that my PhD student Sebastian Lunz did at the very beginning when we started with this. Again, qualitatively, one of the things, because the Wasserstein distance is involved, we could look at this. What happens if you take a gradient step in the direction of the regularizer, and what you can prove here is that if you so if you start out with your distribution of noisy images and you take a gradient step from such a noisy reconstruction in the direction of the now learned regularizer, so of a minimizer of your Wasserstein, of your one Wasserstein loss, and you do this many times, you create a new distribution that is now called P eta, then you can prove that when you do this one step, you actually get closer to your distribution in Wasserstein distance to your distribution of real images. So again, this is not very difficult to show, but it was just nice to see this. And the other one is existence of such an optimal R star. And for that, we needed some additional assumptions on the distribution Pn and Pr, which I've here formulated more in the machine learning sense. Namely, you need what is also in machine learning called the weak data manifold assumption, that your distribution of that should be an R, by the way, PR, that your solution of desirable images is supported on a weakly compact set. And the other one is a small noise assumption where you assume that you can project back from your noisy distribution to the distribution of your desirable images. And if you assume that, then a minimizer or a solution, a regularizer that comes out of this is the distance to this data manifold, which is nice again to think about, this conceptually. Okay, so I think that's all I wanted to say to this part, and then I'll give you a quick. How much more time do I have, Matteo? 15. Okay. Let me stop that now. I know how time is it. Okay. Any questions for the inverse problems part so far? Okay. So then I'll go to the second part, which in a way also links back a little bit to solving inverse problems, but this is now more generally about imposing properties in neural networks directly, because to gain certain properties of the neural network that you want to apply to solve like a classification problem or indeed an inverse problem. And so one topic that appeared a lot, that is again this interface, having this in mind, that this interface between mathematics and neural network is dynamically systems, motivated dynamically systems, parameterized neural networks. And one aspect that we have been interested in, you might have seen this already from the you might have guessed this already from the previous topic, is one Lipschitzness. So this would be something nice to impose. What has been done in this set, what is being done in this setting, usually also we just inherited this from this generative adversarial network, people who have used the Wasserstein distance there before, is just to impose the one Lipschitz constraint or to encourage it by adding by a penalty term that penalizes the Jacobian of R. So yeah, that's but it would be nice to maybe do this directly by designing the neural networks such that they have this property from their parameterization, by imposing that in their parameterization. And a slightly generalized version of this one Lipschitzness, if you want, is this alpha averaging property, which appears again when you think about inverse problems, which appears when you want to set up neural networks to iteratively solve your inverse problem through going through the layers of the neural network. Having that these layers are alpha averaged allows you to show that what you're converging to is a fixed point at the end, if you would go on forever, which of course you don't, but I'll explain this in a moment. Yeah, so this is, sorry, this is just an overview. And the reason Yeah, well, I've explained this from an inverse problems viewpoint. One Lipschitzness, of course, also appears as a mean against adversarial vulnerability. And then I have something, just a one-slider to tell you about approximation theory for one Lipschitz neural networks, if there is time. Okay, so the story for us, at least, I don't know if this is really the first time this appears, but I think Lars Otto and Eldad Haber gave a very nice start to the field within the mathematical community of differential equations, parametrizations of neural networks. And everything started with the so-called ResNet, so the residual neural network, or the class of residual neural networks. So residual neural networks work in the following way. They, so just to say, a neural network is a composition of functions that I call here f theta L, where theta I are parameter vectors, which are exactly the vectors, the parameters that you are learning. These are the free parameters in your model. And the different types of neural networks appear by how you parameterize these functions f. Okay? Residual neural networks are networks where the function or what you learn is an increment from its input. Okay, so when you come to the layer I, you take the output of the previous layer and you add something to it. What you learn now, so which is like, you can think of it as a correction. So you learn a correction from one step to the next. And how you parameterize this or is usually a matrix, or if it's a convolutional neural networks, it's a convolution. If what people call is a dense layer, then it's really a full matrix multiplication, AI with X. You have, so this is learnable, this is where the thetas are. And you have, actually I forgot what this is called now, a bias term, yeah, exactly, this is the B gives it away. So this is what people call a bias term, this is a linear vector that you impose to shift for shifting this to a new position. And then you usually have here a pointwise nonlinearity, like for instance, so-called rectified linear unit, a ReLU, which is looks like something like this. So some kind of nonlinearity that usually works like a thresholding operation. And you could have another linear term here, which is handy for what I want to say later. You have this another matrix multiplication here with a BI. Okay, so the theta is exactly this AI, BI, and beta, capital BI and little BI, and this is what you learn. And you have different theta i's in every layer. So if you look at this, you can also just summarize this within function f theta I. And now the dynamical systems viewpoint comes in by saying, well, this can be just thought of as an Euler step, as an explicit Euler step of size 1 of an initial value problem like this. Okay? Okay, and so now this has opened up a lot of work in this domain by manipulating or by changing the numerical method that you use in order to discretize your dynamical system. Okay, so the whole idea here is that you have a set of parametric functions, f thetas, which is this combination of matrix multiplications and pointwise nonlinearities. And you have a numerical method, like for instance, explicit Euler, and you define your layers as this numerical method applied to a dynamical system that comes from this f theta function. And then you combine this, right? And you can also combine it with the typical, this is more for machine learning people, with the typical things that machine learning people are doing later. Now, how does structure preservation come in? And all of this, in a way, started also with people from what is called geometric integration. So geometric integration is the subfield of numerical analysis where people think about how to integrate differential equations. Is mostly in the ODE. Is mostly actually the community is mostly within ODEs, but there are some also PDE people there. So how to design solutions to differential equations that, when you discretize, still preserve the properties of the continuum model. Okay, like for instance volume preservation as a property here. Okay. So how does this appear here? Well, it just appears by choosing the numerical method to parameterize your residual neural network with a numerical method that you know preserves this property. Okay? So you choose a property like volume preservation, you choose a family of parametric vectors that here I've already written in a way such that I can choose my it fits to the numerical method, to the volume preserving numerical method over here. And then you have a network that, if the property that you're imposing is closed under composition, that's important because you impose this in every layer, and then you want that the composition again has this property. If you have this closed under composition, will also be preserved by the neural network itself. Okay, so this is the whole idea. Now, we have thought about this for one Lipschitz and alpha averaging. So one Lipschitz, I've already said that maybe, so I'll skip that. This was just the motivation, I've said this already. So the one Lipschitz neural network, again, is very simple, is actually a discrete version of non-expansive dynamical systems. Non-expansive dynamical systems are those where the f theta is one Lipschitz. And now you just do the same for its explicit Euler, for instance, explicit Euler approximation. And you get just by a straightforward calculation the constraints you need to impose on your parameterization such that your layer function is one Lipschitz. Okay, and then also the composition of those is going to be one Lipschitz. Okay, which is a restriction on the step size and also on the property, well, depending on what you choose also for your nonlinearity here. Okay. Right, and now alpha averaging, going back to what Stefan has just asked. So alpha averaging means that the function is alpha averaged if there is a one Lipschitz map, and you can write your function f as this linear combination between the identity and this one Lipschitz map. So this is the starting point, and then f is alpha averaged if f is continuously differentiable and has a symmetric Jacobian. Then it is alpha averaged if and only if the spectrum fulfills this property. The spectrum of the derivative fulfills this property. It's very technical, but it comes from the fact that if you want to design iterative schemes that iteratively apply this map f, then having this property allows you to show that you have convergence to a fixed point, okay, which again comes up in this learned iterative reconstructions. You can again easily impose this with just looking at your Euler approximation of the dynamical system by first of all writing it as the Jacobian of this function. And then just imposing the right properties on its spectrum by constraints on gamma and the step size h again. Okay, so this is quite simple. Well, it's a combination between one Lipschitz and you impose additional properties here One Lipschitzness wouldn't be enough. It's actually stronger. One Lipschitzness wouldn't be enough to have convergence to a fixed point. Yeah, but it's weaker than having contractivity, for instance. So yeah. It is very, so this is again yeah, so exactly like here for instance. So it is, yeah, it is usually quite a strong assumption. It's true. And again, this shows you another another challenge of when people think about structure preservation with neural networks is because you don't want to impose too many properties in order for the training data still to have some effect on your solution. I might skip that, but the main thing is convergence. If you have a neural network, for instance, that should denoise an image, so the typical examples that I'm usually showing are connected to imaging or inverse problems. If you have a neural network that you apply iteratively, if you impose this property, this alpha averaging property, you will converge to something. If you don't, you will diverge or by chance maybe converge, but that's very rare. Okay, let me stop here. Let me not talk about this, but this is just the parameterization that we are using for one Lipschitz neural networks is actually dense in one Lipschitz functions. And then maybe don't go there, but I've skipped the whole thing about solving PDEs with neural networks and how structure preservation comes in here. Again, anecdotal, these are just some things that we did in the group. But I think I'll skip that, although it's tempting not to, by just summarizing. So structure preservation in deep learning is motivated by a diverse range of applications. I mainly talked about inverse problems in this talk, and maybe some more generic properties you might want in your neural networks, like stability, or in neural network terminology, adversarial robustness. Mathematics into deep learning and deep learning in mathematics are the two ways how people have thought about this. And we had as an example this variational regularization setting. And for the other one, we had this learned iterative reconstructions. And there are some overall challenges, and I alluded to them throughout the talk, which is this trade-off between structure and expressivity. So how much structure do you impose, and how much freedom do you still allow the neural network in its parameterization? But I think the more crucial one, because that's a decision. This is a modeling decision almost. The more crucial one is how well can I parameterize my structural constraint. And one Lipschitzness, I think, is a good example, because although I have this universal approximation result, in a way it's not so meaningful, because you're never in the setting, right? So you really would need something that gives you as much freedom as possible, is still efficiently computable, but imposes one Lipschitzness, and that's an open problem at the moment, as far as I understand. Okay, thank you very much for your attention.
Carola, for the nice talk. And are there any questions? Okay.
Yeah, thanks. I'm a bit confused about the prefix 1 in the first part of your talk. So when it comes to kind of to L1 regularization, I mean, in imaging, my understanding was always that it works so well because, BV is the dual of Lipschitz, but Lipschitz is really a soup over the gradient in every point.
Yeah.
So it's a soup over many, many functionals, which makes this norm, the unit ball in this norm have many faces. So I think that's the use of L1 in the first part. But the way you use L1 is the prefix 1 is referring to the Lipschitz constant being 1, which in a certain sense since I saw that you're taking the Lipschitz norm with respect to Euclidean norm on the
Yeah.
p-space is quite different.
Yeah, we
So-
thought actually. Sorry, I thought you've referred to this, but we thought a lot about this, and in the end, we actually didn't go there, just maybe because of situational things. But ideally, you would like to choose what we now have as the Euclidean norm as something that is more image related. Like almost maybe another something that again you learn, like a metric that you learn, or something like this. I think this would probably give you much nicer results because again, this is quite generic. Yeah, so I think we just landed in this setting because this is what people in generative adversarial networks used, and we just took that on.
I think perhaps probably I didn't express myself clearly. So the R in the typical imaging, which is the BV norm, is, you know, the unit ball in this infinite dimensional configuration space, or in this high dimensional configuration space, has many faces, because it's the dual norm of an L infinity type norm, and L infinity is in every single point of your lattice. Whereas when you write one Lipschitz, you take that with respect to an L2 and Euclidean norm. So it's much, you know, it's much less. It has much less of this little L1 character, which is promoting sparsity. So that's the confusion which I have. You know, I mean, this in the beginning in imaging, people say they use this BV norm because these L1 type, little L1 type norms promote sparsity. Now, I don't see where this is in this approach because you've discarded, in a certain sense, that character.
What we did for the we did for the one Lipschitzness because of basically pragmatically borrowing these algorithms is that we imposed actually the penalty on the gradient of R is in L infinity, which I haven't. So this I haven't put there, but what you do here instead of this, so what you did, you take this one Lipschitz constraint and you add here on a linear combination between those two distributions, you add an L-infinity penalty on the gradient of R. So this is how you solve this computationally. But again, I don't think this is necessarily the most ideal maybe setup for images. I agree. I mean, but we didn't. Yeah, this is just what we used. But it might be something to think about. Yeah.
Can you go back to the previous slide, the slide where you stopped before this one? So you went back and you stopped at the right.
The variational.
Yes.
This
okay,
one.
This one. Yes.
Yes.
So so V are the learnables, right? The small v are the learnables of the network. So you minimize with respect to V.
Yes.
And V are both in the capital R, so in the regularization, and also in the operator T, right? So my question is, they are the same V, or you have some part of the learnable for the regularization and other part of the learnable in the operator T?
Okay, so I think it's true that we learn R with respect to V, but we are not learning V in the sense that we really learn R and then we plug R into this variational model and then we solve the variational model for V. This is where V, so V really comes out as a minimizer of this.
The rule. Okay.
But you're alluding to something interesting because when we train the regularizer, when we train it, is not aware really of properties of the forward operator. except through maybe indirectly through the training data set, because we usually use the pseudo-inverse here to create the undesirable examples. You could also do something different. What we did a couple of years ago together with Martin Burger is to impose a source condition while training the regularizer. But yeah, so...
Is there a typo in the formula? The loss function should be TU instead of TV. The second summand. Or is V?
No, this is really V. This is V.
Is V, okay.
So V should still should fit the data, right? And you want to regularize it.
Okay, because in another formula you wrote the Y, the prediction as the difference between TU and the noise. So that's why
sorry,
I was
because
confused.
maybe here, right?
Yes.
So here, no, not here, but 1 second. I think here maybe.
Yes,
but
okay.
this is the ideal. So well, here this is the ideal solution,
okay.
right? But now I'm approximating it, and I say I want to approximate. I want to compute. Well, U, not really U, but I want to approximate an approximation of U through minimizing this functional.
Thank you.
Thanks.
Thanks for the talk. I have a question about the second part, the use of the residual networks. So you get with that kind of structures some convergence results, and I was wondering whether. So I guess also that the activation function that you use, you mentioned in one slide, it was really, but I guess that you can extend to more general activation.
It just then changes here. This is just this,
okay.
But you can extend. Yeah. So that's just choosing the typical one.
Okay, so my question was about the applications you looked into. So you looked at. So I understand that with that kind of structure, you get convergence results. But in terms of practical applications, did you observe that in some situations it was more interesting to use other structures than ResNet, and why? So I know that ResNets can be in practice quite interesting because you avoid this problem of this issue of vanishing gradients.
Yeah, exactly.
But for the specific applications you looked at, well, did you observe all the kind of structures that could be more interesting and for which the theory is missing? Fine, but
okay, so this is a good question. So so in the applications we did, ResNets were always also better performing than feed-forward neural networks. Maybe just as a direct comparison, which refers to the one that are not working in an incremental fashion, but just you learn the whole right-hand side. Now there are new architectures around, like transformers, that have quite different structures. And here the dynamical systems viewpoint is still under construction, let's say. So I think they are interesting because they are much more expressive than these residual neural networks are. But they're more complicated because the right-hand side consists of many more operations and also non-local terms. So yeah, okay. I think that is still under construction.
And so, and you do not try to promote sparsity, for instance, so in a sort of intermediate latent space.
I did not, but there are indeed people who are trying to do this. Mainly because of computational efficiency. If you want to create neural networks that are also, when you apply them, are computationally very efficiently computable. And also for interpretability, this could make sense because this one big problem, even if you impose structure in your neural network with deep learning, is that what you get still consists of millions of parameters, and it's very hard to grasp what the mechanisms are. If you have sparsity, there are tools that you can use, I think, also from the classical theory from you know, for instance, eigenfunction decomposition or something like this, that can give you some explainability.
Okay, thanks.
So I think that makes sense, yeah.
Okay, thanks. Any more questions? Okay, so if not, we thank Carola
Thank you
again. The next talk and last talk of this morning is by Felix Otto from the Max Planck Institute of Leipzig, and he will talk about the geometry of dissipative evolution equations.
So Antonio asked me to give a talk on this old subject. And so it's going to be mostly, you know, exclusively more of a historical talk. Unfortunately, there are not that many very young people, so probably all of you will know what I'm going to say. So it's well, then it's, you know, it will get even older. Okay, so let me start with kind of recalling something kind of famous observations by Euler and Arnold on incompressible fluid dynamics. And in order to describe it, let me recall the Lagrangian description. In terms of a map phi, which goes from time and Euclidean space into Euclidean space. And as you know, you can see that you can look at this in two ways. On the one hand, this map kind of collects kind of particle trajectories. If you fix the x and you look at it as a function of time. But on the other hand, it also gives you access to what's called the flow map, which is the opposite. If you fix the time and you look at it as a transformation, as a nonlinear transformation of Euclidean space. And I will be at first interested in the case of no damping. So the inviscid case. No viscosity, zero viscosity, in which case Euler in, when was that, 1757, formulated the model for this. And let me not write down the equation, which he wrote down, and just paraphrase them by saying that essentially what the equations stayed on the Eulerian, not on the Lagrangian level, he formulated them on the Eulerian level, is that the particles move essentially unaccelerated, but they kind of feel a conservative force, which comes from the gradient of the pressure, which ensures that the flow maps are volume preserving. Subject to the flow map being volume preserving. Which I can write like this. So if I take the volume form and I push it forward by the flow map at some given time, then I obtain the volume form. And now the kind of the more geometric observation I want to get at to is by Arnold from the 60s, who realized that in fact what Euler states can be kind of put more succinctly in a geometric way by saying that the flow map as it evolves in time is really kind of a geodesic on the space of volume preserving diffeomorphisms. So on the space or on the manifold, script M of nonlinear transformations of Euclidean space, which are diffeomorphic, such that they preserve the volume, and endowed with a metric from the ambient Euclidean space. And the ambient space, so the tangent space would be kind of vector fields on Euclidean space. And when I mean the ambient space, I mean the ambient L2 space with respect to the Lebesgue measure with values in Rn. And so this is, in a certain sense, almost tautological, but of course he didn't stop there. But he used the fact that this the curvature tensor of this manifold can now be computed with help of Gauss inside between external, exterior and interior curvature. And he pointed out that there is a lot of negative curvature. And then he said, well, so therefore we shouldn't be, in a certain sense, surprised that weather is hard to predict, because negative curvature in a Riemannian setting means that geodesics diverge, which means they kind of depend very sensitively on the initial data. Evolution. So, so that's something, I think a very beautiful observation I wanted to remind you of. And now kind of come to something which is at the other dynamical end. So, so the inviscid case are fluid dynamics where there is no dissipation at all. This is why they're called inviscid, no viscosity, no dissipation. And let's look at the kind of the complete opposite of the dynamical end, when there is kind of where the dynamics are overdamped. And that is the case when you have a flow in a porous medium. And to make this setting more interesting, let's look at the case of a two-phase fluid. So you have two phases, a plus and a minus phase, and they differ in terms of their densities. So let's call it rho plus and rho minus, and mobilities. M plus and M minus. So picture to have in mind that kind of a configuration is described by an interface between the plus and the minus phase. The upper phase is characterized by mobility and the density, and likewise the lower phase. And we have gravity, which acts in the negative z direction. And this is a model which has been formulated much later by Muscat, 34, if I'm not mistaken. And let me do a similar thing as for Euler's equation, as Arnold did for Euler's equation. let me not write down the actual PDE, which Muscat formulated, but let me give you the geometric interpretation of the involution in this sense. And for this, it's convenient to realize that in this setting, you also have two descriptions. On the one hand, you have the one which you already know, kind of the Lagrangian via the flow map or the collection of the particle trajectories. But on the other hand, you can also describe a configuration by specifying its phase configuration, phase configuration. So this you could do by looking at a characteristic function, so a function which just has values 0 and 1 or plus and minus, with the understanding that chi is equal to 1 here in the plus phase and chi is equal to 0 in the minus phase. And of course, they're related in the sense that if you kind of compose the phase distribution with the Lagrangian coordinates, then this doesn't depend on time. And if you insist on the fact that your your flow map at time 0 is the identity, then this must be kind of the initial data or the initial phase configuration. So those are two ways of describing kind of the state of the system. And then what I pointed out a while ago is that it must be 99. That this type of flow can be understood as the gradient flow, at least informally, on the very same manifold, which Arnold considered, with the very same metric, essentially the very same metric, slightly more complicated because I'm allowing for different mobilities. So it's an L2 metric, but now the inner product is not the bare volume form, but it's 1 over m plus, or to be, depends on where you put, like this, m plus chi 0 plus 1 over m minus 1 minus chi 0 dx rd. So that defines the Riemannian structure. And for gradient flow, of course, the most important is to have a functional, of which the gradient flow is the steepest descent. And the functional is just the potential energy with respect to gravity. Which, of course, would be most naturally written in terms of the phase configuration, but let me insist to write it in terms of the Lagrangian, in terms of the flow map. Then it would be given by rho plus chi 0 plus rho minus 1 minus chi 0 integrated against the transformed vertical derivative over the domain, which here is the whole space. So so that's in a certain sense an easy calculation to convince oneself, at least informally, that that the Muscat equation, which I didn't write down, very much like I didn't write down the Euler equation, has this geometric structure. So now the question is, okay, nice, but is there something one can learn from this? Very much like Arnold learned something on Euler's equation, or had some insight on Euler's equation for this. And I think indeed one can learn something from this, and that's what I want to explain now. And that has to do with the fact that there is a highly unstable situation in this two-phase porous medium flow, namely when the heavy phase is above the light phase. So let me, so why interesting? So it's interesting because of the unstable situation. So when the heavy phase, let's say that's the plus phase, is above the light phase, which is the minus phase, so meaning rho plus is larger than rho minus, and the picture is like this. So you start out even with a planar configuration like this, so plus, minus, Z, rho plus mobility, rho minus mobility. Then it's an easy standard applied math calculation that the planar interface is highly unstable, and it's catastrophically unstable in the sense that this evolution as a free boundary problem would be ill-posed because there is no length scale. I mean, this problem still has a kind of a scaling invariance, which is hyperbolic, which means the smaller the wavelength, the larger the growth rate. So, and in fact, in the experiments, and people are interested in this in what's called secondary oil recovery, you find that the interface is highly unstable and forms what's called fingers. So there is something interesting happening here. It's a kind of a problem that generates a microstructure, and you would like to understand as many constraints as possible on the microstructure as you can find. So that's a problem which I got in my PhD thesis from Stefan Luckhaus, which I didn't, I think at the time, even understand. And so for instance, you may ask, can we say something about the average, about the volume fraction? So we seek information or even an evolution that would be very ambitious for the volume fraction. So that's a function which depends on time and space and which has unit interval valued. And in a certain sense, I mean, experts could think about it as being kind of the weak limit of kind of a more and more microstructured characteristic function or evolving characteristic function. And so in kind of in this paper where I made this observation, I proposed a strategy to get to this, to extract some information. And the strategy was the following. So the first step was to reformulate the gradient flow as a minimizing movement. So that is something which, a notion which De Giorgi introduced of a natural time discretization of a gradient flow by a sequence of variational problems, which I'm going to write down in a second. And again, that in a certain sense was, so that I think was in the 90s, and Luigi Ambrosio probably can kind of pinpoint that more exactly, but the very similar things which happened at the same time in geometric analysis. I knew it from Luckhaus-Stutzenhecker, which did about the same thing as Almgren, Taylor, Wang, where they wrote down a minimizing movement scheme avant la lettre for mean curvature flow. So, but in general, that's a very general idea, and that probably was De Giorgi's merit to realize that this is a very general concept which applies to any gradient flow and allows you to set up kind of the gradient flow in a variational sense. So loosely speaking, it's a variational formulation of the implicit Euler scheme. Which comes in the following quite intuitive form. So your configuration at time step k minimizes the squared distance, the squared induced distance on your Riemannian manifold to the previous time step plus the energy functional. And the distance to the previous time step becomes a kind of is endowed with a huge weight because you have to divide it by 2 times the time step size tau. And so that puts you into the framework of calculus variations, and in a certain sense, that replaces a fully dynamical problem by a sequence of variational problems. And once you have a variational problem, you have a very kind of a black box way of relaxing a variational problem in the presence of microstructure, in the presence of weak convergence as opposed to strong convergence. So that's exactly the next step. So relax this variation problem. And what one gets if one does that is the following kind of more tractable algorithm in terms of the volume fraction. So you get that Sk, the volume fraction at step k, minimizes a minimizing movement scheme, which has kind of the same structure. So 1 over 2 tau, that's kind of built in. And then it's 1 over m plus times what is called the squared transportation Wasserstein distance between S and Sk minus 1 plus 1 over m minus. Remember that those are the mobilities, so it's not surprising that the reciprocal comes up in the distance function. 1 minus S, 1 minus Sk minus 1, plus the still the potential energy with respect to gravity, which in terms of S, of course, now is easier to formulate. So it's rho plus times S plus rho minus times 1 minus S dx. And where, as I already said, where W is the, I still call it Wasserstein metric, although that might not be the best name, which for the moment informally I can define. So I'm looking at the squared Wasserstein distance between 2 densities, and following Jan Brunier's polar factorization, I can write it as the info, the min, over all measurable maps phi. It's L2 distance with the identity integrated against one of the densities under the constraint that this measurable, in general not a diffeomorphism, measurable map pushes forward S0 into S1. So that's something I learned from Brenier's work on that one can do these things. I learned from Brenier's work on polar factorization. Which was quite a couple of years older by then. So so that's the relaxation step. And then, of course, in order to infer something like this, you want to let the time step size go to 0 and understand what the limiting dynamics are. And that's kind of the third step. So the third step is to identify the limit as tau goes to 0. And that's kind of what I did in this old work. And I kind of figured out partially rigorously, partially informally, that what you get is an entropy solution of a hyperbolic elliptic system, the form of which was not surprising. I mean, it was kind of formulated, similar equations were formulated under the name of Buckley-Leverett. But the fact that it came out, in particular, the entropy notion came out of this procedure, of this relaxation procedure, was probably not known. And now, what was the prediction of this? So if you take this hyperbolic elliptic system, and again, I will not write down the PDE, because in a certain sense, these structures are more telling than the PDE. You want to start out with unstable stratified initial data. So now I'm kind of just giving you the z-axis, the vertical axis, and you start out with initial data where the heavy phase is above and the light phase is below, so 1 and 0. And now you plug that into this into these equations. And in fact, then the elliptic part drops out because you have translational invariance in the y direction. And only the hyperbolic part matters. And in particular, the entropy part matters because it tells you that this is like Riemann data. So now Riemann, not in the sense of Riemann geometry, but in the sense of systems of conservation laws. And these Riemann data kind of evolve into what's called a rarefaction wave. And that would, for instance, look like this. And it would, fan out linearly in time. And in fact, there's an explicit form for it. You know that the kind of advancing end has the speed of 1/2 m minus times rho plus minus rho minus times t. And the trailing end has 1/2 m plus rho plus minus rho minus times t. So if the mobilities are not equal, it's not a straight line like for Berger's equation, but it has this, if the mobility of m minus, so the light phase, so here is the minus side, here's the plus side. If the mobility of the light phase is higher, it would tell you that this advancing front is further away removed from the original shock than the receding front, which is kind of intuitive physically because the more mobile phase should be able to push ahead quicker than the less mobile phase recedes. I mean, of course, if you change the order, then you would get a concave profile and kind of a different ordering. And in fact, it's nice that kind of these solutions much later kind of appeared as sub-solutions in the jargon of convex integration. And in a certain sense, as extremal sub-solutions in the jargon of convex integration of the unrelaxed problem. So there's work, so the one I know best is by Faustner and Sekilidi, but also kind of the Spanish group, fluid dynamics groups, kind of started with kind of drawing these connections. And so there is indeed something you learn about this. about the original problem, about kind of the growth of the mixing zone, but because wherever S has values strictly between 0 and 1, you expect that there is an underlying mixing taking place. And in fact, with Nicola Gili, who's going to speak at 2, if I understand correctly, probably about something kind of much more recent, we also we reproved this limit here with more modern techniques using from the world of viscosity solutions. And we also kind of observed that in a certain sense, this type of behavior is not so surprising because, so that's with Nicola quite a bit later, namely from kind of a more functional geometric or infinite dimensional geometric point of view. If you look at the energy landscape, so here now I put configuration space S, and here I put the energy axis, and here I put the initial data in the origin of my configuration space, which, if I normalize correctly, has 0. I forgot the z-axis, the z here. Oops. Has 0 energy. Then in energy landscape, if you endow this here with the right Riemannian, with the appropriate Riemannian geometry, so the Wasserstein metric, I mean the two-phase Wasserstein metric, then this energy, so this is an unstable equilibrium. So the energy landscape morally looks like this. But if it were really a classical unstable equilibrium, you would never, nothing would push you out of equilibrium. But indeed, there is a kind of a solution which leads you out of this unstable equilibrium. So this is S0, this is S at some later time. And that has to do with the fact that this energy functional E is, in this point, is not C2. And in fact, it's just 4/3. One can be pretty precise about the intrinsic kind of exponent of this geometry at S equal to S0. And in fact, so to say, the rarefaction solution of this problem realizes that while this is a stationary point, there is a path out of it because your energy landscape has this slightly singular structure. And in fact, there is a relation between kind of this interpretation of entropy solutions and what de Fermat's in the 70s called kind of the maximal entropy production criterion for entropy solutions, which we also kind of point out here. Okay, so that's what one may learn from kind of passing, working out the underlying Riemannian geometry, the gradient flow structure of these dynamics, and kind of going through this step. Now, physically, it's not clear how good this prediction is. So at the time I gave a talk where there were also some people who were actually doing kind of experiments, and so from engineering, and they said, okay, this prediction misses the truth by a factor of 2. In fact, the mixing zone spreads slower by a factor of 2, and that's of course a puzzle. But it's not so surprising because you're looking at kind of an ill-posed variational problem. You're doing something strange to it and extract predictions. But what you really should do is you should kind of consider a physical regularizing mechanism to your evolution equation, like surface tension, like molecular cross-diffusion. And then it might very well be that the solution which ultimately is selected is not this one of maximal spreading, but another one. And with Govind Menon, we wrote a paper which gives an indication that if your regularizing mechanism is molecular diffusion between the two phases, that indeed you get the factor 1/2. But unfortunately, we don't do it for the true model. We do it for a model where Darcy's law, which is sitting in here, is being simplified. And I think one interesting open problem is to really understand kind of what prediction you get from taking a physical relaxation mechanism. That it's mathematically sound in a certain sense now is beautifully shown by this work on convex integration, which indeed for any subsolution, and in particular this maximal subsolution, can construct kind of sequences of solutions of the underlying free boundary problem, weak solutions of the underlying free boundary problems, which have this behavior on average. So that it has a mathematical meaning somewhere is clear. How reasonable it is physically is not clear. How much time do I still have? Okay, I will certainly not. I just have one page more. I wanted to say just a little bit about compressible fluid dynamics. So this was about incompressible fluid dynamics, and I showed you kind of the two sides, the conservative side, the inviscid side, where there is no damping, which was related to geodesic principle, and on the other hand, the polar opposite in terms of dynamics, the completely overdamped case where there is no conservation of momentum, which was kind of mathematical, had the mathematical structure of a gradient flow, and how both, in a certain sense, can be how both geometric pictures, in both cases, Riemannian geometry plays a role, and how both geometric pictures can be used to get some interesting, while not completely satisfactory predictions. Now let me try to do in much less time, also because it's simpler, the case of compressible gas dynamics. First, again, the inviscid case, and then very briefly, the inviscid case, and then the overdamped case, which gives rise to the porous medium equation. Okay, so unless there are questions here, I would move on to the compressible single phase case. So, and so therefore it's better now to think about the gas. And in this case, while of course compressible gas dynamics is kind of mathematically a very subtle area because of shock formation and all the kind, let me ignore these subtleties and just say that the inviscid case can be described by least action principle. So by writing down a least action functional on curves of configurations, or a Lagrangian, and that least action functional is given by you take the kinetic energy, rho 1/2 u square. Now I'm writing down the Eulerian velocity u. So that's the kinetic energy. If I'm thinking of, if I'm kind of hardwiring into the ansatz the equation of continuity or mass conservation, and then because it's the Lagrangian and not the Hamiltonian, I have to take minus the potential energy, and that has the form of some internal energy which depends on the density in a pointwise way times Ex. So that's the potential, in this case, internal energy, here with a kind of very simple law. And then I have to take this and integrate against time, and that would be the least action functional. And of course, experts already, I guess by now, most in the audience already recognize that this part of the problem is nothing else than a kind of a naive version of the Benamou-Brenier Eulerian formulation of optimal transportation, which was 2000 or 99, I don't quite remember. And so that's all I want to say about the inviscid case, although one could say many things about the inviscid case, that there is a least action principle. And I want to right away jump to the overdamped case to somehow to complete the matrix and give you kind of a similar story as before. So again, we do that in a porous medium. And that's described by what's called Darcy's law. Now I write down everything in the Eulerian setting. So from the least action principle, you would get that you would get Newton's law in the certain sense that the acceleration mass times or mass density times mass density times acceleration is equal to force. And in the overdamped case, which in a certain sense is much less universal, you get that the velocity, not the acceleration, is proportional to a force. And the force here is a potential force which arises, so I forgot to write down this notation, this is a functional E of rho, which arises as the functional derivative of your potential or internal energy. And of course, it goes in the negative direction. And since this is not first principles, there is a factor of proportionality, which is called the mobility, might even be anisotropic, depending on the structure of the porous medium. But we've had mobilities already. But now it's a single mobility because it's a single phase. And so, of course, this is something you can compute. So let me continue here. This is equal to minus m times the so the functional derivative, so let me do it in two steps. So it's minus m times the gradient of E prime of rho, E prime being the derivative of this scalar function which associates an internal energy density to a mass density. And that's equal to minus m times rho, m E double prime times rho grad rho. And now if you take this identity and you plug it into the continuity equation, you get what's called the porous medium equation. With an osmotic pressure, so a density pressure relation that follows from that relation, which is given by pi prime of rho is equal to m rho E double prime of rho. And that's called the porous medium equation. And that's a nonlinear elliptic, nonlinear parabolic PDE that has been studied already since probably Barnblatt is perhaps one of the first names. I mean, definitely longer than half of a century. And so with kind of this Wasserstein geometry in mind, in a kind of a later paper, I observed that, and that was in the end, a rigorous proof that the porous medium equation, let me abbreviate it like this, that the porous medium equation is a contraction that is a contraction was not new. It was known that it's a contraction in L1 by the variable doubling method, for instance. It was known that it's a contraction in H minus 1, because in fact it can also be seen as an H minus 1 gradient flow. But in fact, it's also a contraction in Wasserstein. So, and that's not surprising, because of two observations. The first observation is that the porous medium equation, in fact, is the limit as the time step size goes to 0 of a minimizing movement scheme with distance function or squared distance function given by 1 over the mobility times the square Wasserstein distance. And this energy functional, so the internal, the physical energy. And that, in a certain sense, is a variant of the work with Jordan Kinderlehrer, a nonlinear variant of the work with Jordan Kinderlehrer, which was published earlier, but and so there is this remark, and the second observation is that this internal energy functional is intrinsically or geodesically convex. And that, in fact, is just a reformulation of what McCann called displacement convex. And so, which is, in a certain sense, just equivalent to saying that this functional is convex under dilations of space, which comes with the rescaling of densities. So that was Robert McCann's PhD thesis. And so that's, so therefore, from kind of a geometric picture, this contractivity is not surprising, because now, as opposed to the two-phase porous medium equation, if here I put the configuration space, and here I put the energy function, it's a nice convex set. And therefore, if you look at the steepest descent in a convex landscape, you get contractivity. And in fact, that can be used to show that the asymptotic behavior in a pretty quantitative way, that the asymptotic behavior of the porous medium equation is given by what is called the Barnblatt solution, so the self-similar mass-preserving solution. So that was one observation from this paper. And the second observation, and that's what I want to close with, is that, in fact, this much simpler single-phase Wasserstein geometry, so if you look at the space of densities or probability densities endowed with the Wasserstein metric, is nothing else than an isometric submersion of a Euclidean structure. And the Euclidean structure is very explicit, and the isometric submersion is almost kind of too easy to state. So you go back to the ambient space, which Arnold looked at, and where you looked at all kind of perhaps I shouldn't use this. No, yeah. So he looked at the space of transformations of Euclidean space, and he borrowed the metric from the ambient space, L2 space. And if you take this kind of metric or Riemannian geometry, and you look at the following map, which associates to this the push forward of the volume form, or a more general reference measure, then you get the Wasserstein space. Let's say we're on a torus, so that this is a finite space. So this map is a Riemannian submersion. So the Wasserstein geometry is a geometry which naturally arises from Euclidean geometry under this operation. And in a certain sense, that's dual to the observation of Arnold. So Arnold looks at the pre-image under this map because he fixes the volume form. And there he gets a lot of negative curvature, whereas it's built into a submersion that whatever you have here has more curvature than that. And since this has zero curvature, this must have non-negative curvatures. The consequence of this was that, at least informally, sectional curvature, of which you can write down a formula, is always non-negative. And in fact, it's mostly strictly positive if you're in dimension larger than 1. And this informal observation, where I used O'Neill's formula to write down, very much like Arnold had used a version of Gauss formula to write down what the sectional curvature is. I used what's called O'Neill formula to write down the sectional curvature on Wasserstein space, and you formally see this non-negativity and the positivity and the generic positivity that was kind of made rigorous by Luigi, Nicola, and Giuseppe. I think it made it into their book, and they made this rigorous by looking at Alexandrov triangles. So I think that closes the story with kind of connects back to the observation of Arnold. There you have mostly negative and very negative curvature. Here, because it's dual to it, you have only non-negative or mostly positive curvature. And here, as opposed to in Arnold's case, one can really pin it down in a rigorous sense by looking at triangles, so just appealing to the metric structure and not any differential structure. Okay, so let me stop here.
So thanks, Felix, for the nice talk. Are there any questions?
Yeah, I have a vague one as non-expert about the time discretization. I was wondering if one means to catch somehow finer and finer structures that are forming. Would it make a difference if you take a time discretization, which is maybe like dyadic, instead of taking the same step somehow? Maybe dyadic to some extent and...
So, I mean, leaving aside the question that both would be cheating, that might be actually a good idea to zoom in, because in a certain sense, perhaps not here, but in other cases, you would expect that the microstructure which evolves has a certain statistical self-similarity. And that one you would capture in a more pristine way by going to kind of geometrically increasing time steps and then letting kind of the time step size to go to 0. So something like this, we thought about it in coarsening problems, which also have kind of a gradient flow structure, but we never made it work. And but I think it's a very natural thing to do.
Thanks.
Other questions or comments? Okay. So if not, we thank Felix again.